Carbon. It's one of the most abundant elements on Earth, is essential for life and found in various forms and compounds all over the planet. Pure carbon can exist in many different states, known as allotropes, and until very recently, the only known examples were amorphous carbon, better known as coal, which is made of carbon atoms arranged randomly with no consistent structure or order, diamond, which is composed of a giant lattice of covalently single-bonded carbon in a tetrahedral structure, and graphite, which is composed of multiple layered sheets of hexagonally arranged carbon atoms, essentially forming sheets of fused benzene rings known as graphene, which are held together by weak van der Waals forces to form graphite. In this video, we'll be discussing the newest addition to the group, carbon fullerene. In 1984, scientist Harry Kroto teamed up with Richard Smalley and Robert Curl, who had a machine that used lasers to blast atoms off objects and direct the clusters that came off into a mass spectrometer to measure their molecular masses. Kroto wanted to try using graphite in the machine, but when they did, they found unexpectedly large molecules, with masses corresponding to C60. However, they soon worked out a better way of synthesizing their new molecule. Touching the ends of two graphite rods together, while attached to a power supply, created an arc, the soot from which could be filtered to find small quantities of C60, which later became known as Buckminster fullerene, or buckyballs. Analyzing the structure of the C60 molecule showed it to be spherical, with its surface being composed of 20 hexagonal faces and 12 pentagonal faces. This particular configuration of atoms happens to be identical to the shape of a football. Unlike graphite, the hexagonal carbon rings do not share electrons as a giant aromatic structure, with Buckminster fullerene instead tending to react similarly to an alkene. Further experiments and analysis showed that this was not the only new carbon allotrope to be found, with C70, an elliptical variation of C60, being found, along with many other spherical molecules, even as small as C20. The three were awarded the Nobel Prize in Chemistry in 1996 for their discovery of fullerenes. The shape of fullerene allows it to encapsulate small molecules as a molecular cage. The inside of fullerene is very unreactive, so the enclosed molecule will remain untouched, but the outside is very reactive, allowing for it to be functionalized, having atoms or chains of atoms added to it to fit specific needs. When a molecule is put inside a fullerene cage, this is referred to as endohedral fullerene. Many different atoms can be put inside fullerene, including noble gases, metals, and even reactive nitrogen atoms. Since no molecular cages had ever been seen in chemistry, new notation had to be made. For example, Cu at C60 represents a copper atom enclosed inside a buckyball. Taking the C13 NMR of fullerene shows only one peak, as every single carbon atom is in the exact same environment. This is referred to as the one-line proof, as the presence of only the one line proved that they had correctly predicted the structure. So, now that we know how to make Buckminster fullerene, what can we do with it? Due to its spherical shape, it was originally thought Buckminster fullerene would be a useful lubricant. Unfortunately, it turned out that the outside of fullerene is so reactive it would bind to the two objects, holding them together instead, making it a terrible lubricant. Atomic homing beacons, such as helium, which emit detectable radiation, can be put inside buckyballs and used as chemical tracers in medicine. Buckyballs also absorb sunlight very well, suggesting that they may be a useful molecule in solar panels. It accepts electrons easily, making it very useful in electron donor and acceptor-based solar cells. Buckminster fullerene has also led to the discovery of nanotubes, which have a huge range of potential uses. Unfortunately, no consumer quality or cost applications of Buckminster fullerenes have been found yet, but research is ongoing, so while we don't see any in use around us right now, we may well begin to see them in technology soon. This video was brought to you by Video Project Group B4. Thanks for watching.